Hello, I'm Shraddha Lakshmi from first year MCA Department of IT at Kannur University. Today I will explain CPU scheduling algorithms in monoprogramming and multiprogramming environments. What is CPU scheduling? CPU scheduling decides which process should execute next. The main goal is to improve CPU utilization, reduce waiting time, and ensure the system performs smoothly. Maximum CPU usage, maximum throughput, minimize waiting, turnaround, and response time, and maintain fairness are the objectives of scheduling. What is monoprogramming? In monoprogramming, only one process exists in memory at a time. No preemptions or switching. Now let's look at scheduling in monoprogramming. Since one job is present, CPU scheduling is very simple. Only one job, since FIFO queue, no process replacement and no context switching. This means that whichever comes first runs first with no interruption. Characteristics of multiprogramming scheduling are no preemption, no multitasking, and high CPU idle time if job waits for IO. Now let's discuss what is multiprogramming. Multiprogramming loads many processes in memory and switches between them. Multiple jobs appear side by side instead of one. Multiple processes compete for CPU, so selection policy is required. This is the need for scheduling in multiprogramming. These are some of the important scheduling terms. Arrival time. The time when a process enters the ready queue. CPU doesn't execute it immediately unless it's the first or highest priority process. Burst time. The time a process requires on the CPU to complete execution does not include waiting or IO time, only actual CPU processing. Start time is the time at which a process starts execution for the first time on the CPU. Turnaround time is the time a process spends in the system from arrival to completion. Calculate the turnaround time by subtracting the arrival time from the completion time. Waiting time is the time a process spends waiting in the ready queue, not executing. Waiting time can be calculated by subtracting burst time from turnaround time. Response time is the time from arrival until first execution of process. It can be calculated by subtracting arrival time from the start time. Algorithms can be divided into two types: non-preemptive algorithms and preemptive algorithms. Non-preemptive algorithm consists of FCFS, SJF, Priority, and HRRN. FCFS scheduling. FCFS stands for first come, first serve. It works like a queue in a ticket counter. First arrival runs first. This is an example of FCFS scheduling for 4 processes. Since all arrive at time 0, they are executed in order P1, P2, P3 and P4. The table shows each process's start and finish time, and the Gantt chart visualizes their execution from time 0 to 12. Using the chart, we can calculate waiting time as the start minus arrival and turnaround time as the finish minus arrival. The waiting time are 0, 4, 7 and 11, giving an average waiting time of 5.5 units. Turnaround times are 4, 7, 11 and 12, so the average turnaround time is 8.5 units. SJF scheduling stands for shortest job first. It selects smallest burst time. This figure is an example of SJF scheduling where processes with the shortest job time are executed first. All processes arrive at time 0, so the CPU picks them in burst time order: P2, P4, P3 and then P1. The Gantt chart clearly displays their execution sequence from time 0 to 12. Waiting time is calculated as start time minus arrival time, giving values of 0, 1, 3 and 6, resulting in an average time of 2.5 units, which is much lower compared to FCFS. Turnaround times are 1, 3, 6 and 12, giving an average of 5.5 units. This shows how SJF reduces waiting time by prioritizing shortest job first. HRRN scheduling. HRRN stands for highest response ratio. Ratio is calculated by adding waiting time and burst time and dividing it with burst time. This figure shows the example for HRRN scheduling where the processes with the highest response ratio gets executed next. Since response ratio is equal to waiting time plus burst time divided by burst time, processes with longer waiting benefits gradually reduces starvation. Here the execution order becomes P1, P3, P2 and then P4 as shown in the Gantt chart. The waiting times recorded are 0, 2, 4 and 7, giving an average waiting time of 3.25 units. Turnaround times are 2, 4, 7 and 8, resulting in an average turnaround time of 5.25 units. This scheduling improves fairness by balancing burst time and wait time. Next is priority scheduling. It is based on highest priority. The job with highest priority is done first and the jobs with low priority waits. This is priority scheduling where processes are executed based on priority instead of arrival or burst time. The priority order here is P4, P3, P2 and P1, which is shown clearly in the Gantt chart. From the execution timeline, we calculate waiting time and turnaround time for each process. The waiting time are 0, 3, 4 and 7, giving an average waiting time of 3.5 units. The turnaround time are 3, 4, 7 and 12, resulting in an average turnaround time of 6.5 units. This highlights how scheduling based on priority can significantly affect waiting and overall response time. Now the second category, preemptive algorithms. It consists of round robin, SRTF, preemptive priority, multi-level queue and MLFQ. Round robin. In round robin, each processes get a time slice called quantum. This example demonstrates round-robin scheduling with a time quantum of 5 milliseconds. Each process gets equal CPU time in cyclic order, preventing starvation and improving response time. The Gantt chart shows how CPU time is repeatedly shared among P1, P2, P3 and P4 until all processes finish. From the completion times, we calculate the turnaround time and then derive waiting time by subtracting burst time. The average waiting time comes to 11 milliseconds and the average turnaround time is 19 milliseconds, showing how round robin balances time fairly among processes in a time sharing system. SRTF. SRTF stands for shortest remaining time first. It is the preemptive SJF. The CPU always runs the job with the smallest remaining time, so arriving short jobs preempt longer ones. You can see P1 is preempted when P2, P3 and later P4 arrive. From the Gantt chart, the finish times are P2 equal to 2, P3 equal to 5, P4 equal to 7, P5 equal to 13 and P1 equal to 20. That yields an average turnaround time of 7.4 units and an average waiting time of 3.4 units. SRTF minimizes average waiting time compared to FCFS but can cause frequent preemptions and possible starvation of long jobs. Next is preemptive priority scheduling. When a new job arrives with higher priority, it interrupts the currently running job. The Gantt chart shows several preemptions and resumed executions. From the finish times, we compute turnaround time and waiting time for each process. That yields average waiting time 4.8 units and average turnaround time 8.2 units. Note how highly priority or early arriving jobs get faster service while lower priority jobs, here P4, can end up waiting longer. That's the trade-off with preemptive priority scheduling. Multi-level queue. In multi-level queue, processes are divided into separate queues like system, interactive and batch jobs. This is a two-level multi-level queue scheduler. Q1 with high priority uses round robin with quantum 4 and Q2 uses round robin with quantum 3. New jobs join their assigned queue at their arrival time. The scheduler always serves Q1 whenever it has ready jobs. Q2 runs only when Q1 is empty and Q1 arrivals preempt Q2. Because of that priority preemption, some lower priority jobs, example P2, wait a long time before getting CPU slices. From the simulated Gantt, we get average waiting equal to 11 and average turnaround 18.2 units. This shows the responsiveness benefit for high priority jobs and the potential for increased waiting for lower priority jobs under static multi-level queuing. Now the last one, multi-level feedback queue, MLFQ. Unlike previous, this shows arrows between queues. If a process uses too much CPU, it moves to lower queue. If less CPU usage, more upward. This flexible movement improves fairness and efficiency. Here, new jobs enter Q0. Round robin with 8 milliseconds. If they don't finish in 8 milliseconds, they are moved down to Q1 round robin with 16 milliseconds, and long running jobs eventually go to Q2 FCFS. This lets short jobs finish quickly while preventing starvation by gradually aging longer jobs. To evaluate performance, read completion times. The average waiting time is 14.67 units and the average turnaround time is 26.33 units. Here we are comparing monoprogramming and multiprogramming. In monoprogramming, only one process stays in memory at a time, so the CPU has to wait whenever the process waits, leading to low CPU utilization. Since only one process is running, scheduling is simple. There is no preemption and no context switching. This type of system is best suited for simple and older systems. In contrast, multiprogramming allows multiple processes to reside in memory simultaneously, which keeps the CPU busy most of the time, resulting in high utilization. However, because many processes are active, scheduling becomes more complex and preemption and context switching are used frequently. This method is widely used in modern OS for better performance and efficiency. This chart helps decision making when selecting a real-time scheduler. In summary, monoprogramming does not require complex scheduling, while multiprogramming needs algorithms to manage multiple processes efficiently. Each algorithm suits different system types.